Okay. Recall that the boiling point of liquid. So that we discussed already here. This is the boiling point. It is the temperature at which the vapor pressure of any liquid becomes equal to the atmospheric pressure. It's called as boiling point. Okay, now how boiling point get elevated means how it is going to increase. Suppose we have water and we know the boiling point of water is 100 degrees Celsius. But suppose if we will add here non-volatile solute beta. If you will add non-volatile solute, so vapor pressure of that solution is going to decrease, due to which let me make you understand with the help of example beta. Wait. Have you wrote that definition of boiling point, everyone?
Yes, sir.
Okay. Now I will make you understand how the temperature is going to, or boiling point temperature is going to elevate, means increase for the solution. Okay. Again, we have to discuss about non-volatile solute beta. Non-volatile solute. Okay. So I'm drawing here one container. Okay, here we have one container, and here we have the liquid surface. So let me draw liquid surface in brown like this. Okay, and surface particle I'm going to draw with different color beta. Okay, and I am using here green color for surface particles like this. Okay, and I have covered that container. Like this. Let me draw a little neat diagram. Like this. Yeah. Okay. And I have covered that container like this completely. Okay. And I have maintained the temperature here. Okay. Here temperature is constant, and which is of 20 degrees Celsius or 25 or 30, any temperature you can take. I'm just taking 30 degrees Celsius. In the temperature, I have just made the constant temperature here in its surrounding. Okay, this is surrounding, and I have maintained temperature here of 30 degrees Celsius. So we know that liquid means water is volatile in nature. Volatile, right, everyone? So the liquid particles are going to evaporate, no? Is it? Everyone keep replying.
Yes, sir.
Yeah, so these are nothing but the vapors. Okay, now I'm just considering the vapor pressure here is about someone is in waiting room. No, wait. Okay, so I'm considering vapor pressure of that particular container. Okay, so here we have water, and we know water is volatile in nature. Due to volatile, the liquid water is going to evaporate here, right? So I'm writing here the process called evaporation. It is evaporation process, right? And I'm just considering this. See, after some time, what happens? When temperature is being constant here, so rate of evaporation and the rate of condensation means the same time, if temperature is constant, then same time these vapors are going to condense into liquid form also. So I'm writing here condensation also. Condensation, right? So here evaporation as well as condensation, both the process takes place simultaneously. Is it everyone? Keep replying, beta.
Yes, sir.
Yes. See. So what happens after some time? Okay, if temperature is constant here, you can take any temperature, 30, 20, 15, any temperature. So I have taken 30 degrees Celsius temperature here. So at a constant temperature, so this is temperature is constant. So I'm writing here constant temperature. Constant temperature. So if temperature is constant, then after some time, the rate of evaporation. So I'm writing here rate of evaporation. Rate of evaporation becomes equals to the rate of condensation. The rate of condensation. Okay. In last colligative property, also we discussed the same thing, beta, right? The rate of evaporation becomes equals to the rate of condensation, and it is possible only at a constant temperature. So I'm writing here at a constant temperature. At a constant temperature. Okay, that state is called as beta equilibrium. That state is called as equilibrium. Right, everyone? Equilibrium. Any doubt till here? To reply, beta. Are you there, everyone? Okay.
Yes, sir.
Okay, okay. So condensation and evaporation becomes equal when there is a temperature constant. So, okay. Now at equilibrium, the pressure applied by the vapors on the surface of liquid. This is the surface of liquid inside the container. Surface of liquid. Wait, someone is in waiting room. Yeah, Ajay just joined the class. Okay. So now at equilibrium, at equilibrium, the pressure exerted by vapors on the surface of liquid, is called as vapor pressure. Understood, everyone, what is vapor pressure is?
Yes, sir.
Okay. And we have already gone through about the definition of boiling point. What is definition of boiling point? When vapor pressure of the liquid becomes equals to the atmospheric pressure at a particular temperature, that temperature is called as boiling point. Okay, now I'm just discussing the normal condition, beta, normal condition. Now I'm going to heat that water. Okay, now temperature is not constant and it is going to increase. Again, someone is in waiting room. Oh, wait. Okay. Now I'm going to heat that liquid beta continuously. Okay. So we know if we will heat the temperature of the water is going to rise up to 100 degrees Celsius, na? Right? Is it? And at 100 degrees Celsius temperature, water is going to boil, right? That temperature Okay, that particular state, beta, at that particular state, the vapor pressure of liquid becomes equals to the atmospheric pressure. Atmospheric pressure, beta. Understood? At 100 degrees Celsius temperature, vapor pressure of the water becomes equals to the atmospheric pressure. Then liquid going to turn into gaseous form, beta. That temperature is called as its boiling point. Now, I'm just considering, see, at 30 degrees Celsius, suppose the vapor pressure is 30 mmHg, millimeter in mercury. Okay, this is the barrel or like measuring pressure measuring device we are having. Okay, at 30 degrees Celsius, I'm just considering it is 30 mmHg. And atmospheric pressure, I'm just considering it is 100 mmHg, 100 mmHg. Okay, and the temperature we are going to increase. Okay, see here it is 30 degrees Celsius and here it is 100 degrees Celsius. I'm just considering normal condition, not extraordinary condition. I'm just considering normal condition. So that means we had to rise the temperature from 30 to 100 degrees Celsius. Then the temperature due to rise in temperature, vapor pressure of the liquid again increases from 30 mmHg to 100 mmHg, right? Everyone, is it or not? Is
Yes,
it
sir.
everyone? That
Yes,
means
sir.
from 30 to 100 degrees Celsius, we had to rise pressure up to 70 mmHg, no? mmHg in order to make it 100 mmHg, right?
Yes, sir.
Okay. So this is the normal condition. But now we have added non-volatile solute here. Non-volatile solute means what? Temperature is constant here, starting temperature. Like I'm taking H2. No, not H2SO2, it is acid. Yesterday we have taken copper sulfate. No? So we will take copper sulfate only. CuSO4. This is the copper sulfate beta. And we know copper sulfate is what? Non-volatile. Non-volatile compound or salt you can write. Right? So now we have added copper sulfate in that solution. So copper sulfate is going to dissolve completely in water and particles of the copper sulfate going to distribute all over the solution uniformly, right? Is it or not?
Yes, sir.
Yes. So suppose at starting there are 100 particles on the surface of water. Okay, and the rate of evaporation I'm just taking 10 particle per second.
Sir, good evening.
Very good evening, sir.
Good evening, children. Good evening, students.
Good evening, sir. Good
Good
evening.
evening.
Evening, sir.
Hope you all are enjoying the session. Now we have made some changes slightly. Some changes. This experiment we are going to continue for 1 month, and we will see like daily basis classes will be happening for all the 3 subjects. And I request all of you to join the class on time. And
Just
we
do
require your
reply in class. Yes, sir. Two-way communication
Yeah.
must be there.
we require your complete participation so that whatever you have a doubt, you can get clarified. Teacher will also be interested, and especially teachers are happy with all of you. And one request which I would be always mentioning to all the students, please turn on your camera. You have any problem in turning on the camera? So please turn on the camera so that you by default you become attentive in the class. And you have any concern, interact with the teachers. No? They are all highly skillful and knowledgeable teachers. Okay, children, please turn on your camera, beta. Okay, sir, take over, please.
Yes,
Ensure
yes.
children to turn on. If they are not turning on the camera, then you can mention straight away, take the screenshot and post in the group. I'll discuss personally to their parents.
Okay, sir. Okay. I'll do. Everyone, you can like turn on your cameras, beta. Okay, so we'll continue the session. See, uh, we have already discussed about vapor pressure of the pure solvent, right? Of water. Here we have taken water because generally we know water has boiling point 100 degrees Celsius, and we are very much familiar about water. That's why I have taken example of water here. Okay. And we were required to raise the pressure from 30 degree to 100 mmHg, no, 30 mmHg to 100 mmHg in order to make the vapor pressure of liquid equals to atmospheric pressure. So it is just we are taking example. Huh? Now, what we have added here? Copper sulfate, which is non-volatile solute. If you will dissolve copper sulfate in water, so particles of copper sulfate, they are going to distribute all over the solution, right? So before adding copper sulfate, suppose we have taken 100 particle on the surface, out of which 10 particle they are going to evaporate per minute. I'm just taking 10 particle per minute was the rate of evaporation beta. But out of which, see, few of the particle of copper sulfate, they are going to acquire space on the surface also, right? If we have added copper sulfate in water, their particles are going to uniformly distribute all over the solution. So few of the copper sulfate particles are going to acquire space on the surface, right, everyone? That means the number of particle of the water going to decrease on the surface when we will dissolve copper sulfate in water. Is it or not? Is it, everyone?
Yes, sir.
Yeah. So due to decrease in number of particle of the solvent or volatile solvent on the surface, due to which the rate of evaporation is also going to decrease. Rate of evaporation we have taken like 10 particle per minute. Now it will going to decrease. I'm just taking example 8 particle per minute. So rate of evaporation is going to decrease. Due to decrease in rate of evaporation, number of vapors present on here in that container is also going to decrease. If pressure, sorry, if number of particles are going to decrease, so obviously vapor pressure is also going to decrease, na? Right? Is it or not? That we discussed yesterday also, lowering of vapor pressure. So here lowering of vapor pressure takes place. Now, if vapor pressure like decreases, I'm just considering the decreased vapor pressure of 25 mmHg at 30 degrees Celsius. The temperature is constant here. But initially when it was only pure solvent, so pressure was 30 mmHg. But after adding non-volatile solute, the pressure has decreased up to 25 degrees Celsius, 25 mmHg. Now we had to raise the pressure from 25 to 100 mmHg. So now here we had to increase the pressure up to 75 mmHg. Na? Means extra 5 mmHg we had again increased, and for that we do require extra temperature or extra heat beta. That means if water was boiling at 100 degrees Celsius, but now solution is going to boil around 102 degrees Celsius. Means temperature of boiling point has increased by 2 degrees Celsius. That increase in temperature is called as elevation in boiling point. Why elevation of boiling point takes place? Due to lowering of vapor pressure. Okay, and why lowering of vapor pressure takes place? When we added non-volatile solute in water or solvent then. Is it, everyone? So this is all about elevation in boiling point. This is the process how boiling point elevates. Understood, everyone? Keep replying, beta.
Yes, sir.
reply. Everyone ask. I got disconnected suddenly. Okay. Now any doubt beta here? Why like boiling point get elevated or increases? Understood that?
Yes, sir.
Okay. See, we have initially we had water, so its boiling point is 100 degrees Celsius. Okay. Because of adding non-volatile solute, vapor pressure is going to decrease, which is called as lowering of vapor pressure. Due to lowering of vapor pressure, we had to increase temperature in order to increase the pressure up to 100 mmHg. It is like we have taken example here. Okay, that means we do require extra temperature to raise the temperature up to 100 mmHg so that the vapor pressure of that solution becomes equal to atmospheric pressure. That's why that extra required temperature is nothing but the elevation in boiling point. So water used to boil at 100 degrees Celsius, but after adding copper sulfate or any non-volatile solute in it, it is going to boil above 100 degrees Celsius. It may be 101, it may be 102 degrees Celsius, it may be 100.5 degrees Celsius, but it will boil above 100 degrees Celsius. Okay, and that elevation in boiling point depend on the amount of solute we are going to dissolve. Because if more solute we are going to dissolve, more particle on the surface is going to acquire, due to which more water is going to water particle are going to decrease on the surface, which causes more lowering of vapor pressure and do require more temperature to boil the solution. Okay, everyone. Yes, now we will discuss from the notes now. Again, the same thing we have discussed in lowering of vapor pressure, more or less similar here we have. Okay, so here we have del TB. It is 0, not del TB. First, we will discuss about the vapor temperature or boiling point temperature of pure solvent. It is represented by T0 beta. T0. T is temperature, 0 is pure, means 0 concentration, means pure solvent you can say, and B is the boiling point. After adding solution, okay, like after adding what? Non-volatile solute, the boiling point of the solution becomes TB beta, that one. TB. And we know TB is always greater than T0, right? That means we have to subtract boiling point of pure solvent from the solution. So we will get change in or elevation in boiling point. So here delta TB is called as elevation in boiling point. Okay. Okay, everyone. I hope you understood that. See, what is T0B? It is boiling point PPT, boiling point of pure solvent. Pure solvent. So, pure solvent. Okay, after adding non-volatile solute, it becomes TB. Is what? Boiling point of solution. Okay, and we know it is greater than that one. So we can calculate delta T. Del TB is equals to what? TB minus T0. Okay, suppose we have taken it is 100 degree and it is 102 degree. So del TB will be 102 minus 100. So it will be 2 degrees, right? Like this. Okay, everyone.
Yes, sir.
Okay. Now we have to calculate molar mass also. Okay, so for that we have to compare with the mole fraction. Okay, so here we have like a graph for the same. So here we have boiling point here. See, here we have bit of vapor pressure. So first here we have solvent. So its vapor pressure was more. Okay, as compared to here and here, vapor pressure is going to high for pure solvent. So it is going to boil at over here only that particular temperature. But now we have added non-volatile solute, so vapor pressure is going to increase. So it is decrease. So it is going to decrease up to here beta. Okay, and now if it is going to boil, it is going to boil at that particular temperature, the LTP. Okay, the difference from here to here is called as LTP. It's called as delta TP. Okay. Okay, everyone. Do reply. That
Yes,
one
sir.
is delta TP. Okay. So as stated, okay, now, and we already know lowering of vapor pressure. We already calculated yesterday in last class beta. What we have calculated? Change in pressure. Okay. Lowering of vapor pressure is directly related with the mole fraction of solution and means product of mole fraction of solute to the what vapor pressure of pure solvent. Okay, so it is a product of that is equal to the lowering of vapor pressure we have calculated in last class only. Okay, so here, see, here it is given beta. The atmospheric pressure is 760 mmHg. Yeah? I have just taken 100 degree. It is for in order to understand. Okay. So now we have to compare with the mole fraction beta over here. Where? Over here. See, the delta TB, okay, is directly proportional to the molality. Is a small m is called a beta molality. Okay, molality of the solution means if we are going to dissolve more solute, more temperature is going to rise for boiling the substance. Okay, now we have to convert that sign, okay, proportional sign to equal sign. So whenever we are converting that into equal sign, we have to multiply it by constant, right? Right, everyone?
Yes, sir.
Yes. So whenever we are going to convert proportional sign into equal, we have to multiply by constant. So here that constant is called as ebullioscopic constant beta. Ebullioscopic constant. Just do remember the name for that constant. Okay, or it is called as molar elevation constant or ebullioscopic constant. Okay, if suppose molality of the substance is 1 beta 1. Okay, if 1 molar solution we are going to form by dissolving non-volatile solute in volatile solvent, then okay, then change in temperature, okay, or rise in temperature or elevation in boiling point, which is equals to the constant, which is not going to change when we are going to prepare 1 molar concentration of the solution. Then okay, but if it is not equals to 1, okay, then we know molality formula beta. What is the formula of molality? Yes, here it is given molality equals to what? Where it is given over here, that one. Okay, mass of solute divided by molar mass of solute in kg beta, kg. Okay, here. So we have to convert that kg. Okay, so here we have like multiply divided by 1000, then we will get any gram substance into the molar form beta or kg form, right? See, suppose we have 50 gram, so we have to divide it by 1000, then we will get in kg form 0.05 kg like this. Is it or not? Is it, everyone? Yes. Okay, so here we have molality is equals to moles of the solute divided by mass of the solvent in kg. Okay, so here we have formula for molality. So don't go for the derivation and all, just do remember small m means molality equals to 1000 into mass of the solute divided by molar mass of solute into mass of solvent. That's all. Okay. Now we have already gone through that. Delta TB is equals to Kb into M. M is what? Molality. So instead of that, just put that value, you will get the formula. So now we will get delta TB is equals to Kb into 1000 into W2 divided by capital M2 into W1. Only that formula you have to remember, that's all, because you will get numerical on that basis. You are not going to ask to derive the equation. Okay, you just need to remember that formula. Okay, so where delta T is elevation and boiling point, K is ebullioscopy or molar elevation constant, W2 is mass of the solute, M2 is molar mass of solute, and W1 is mass of the solvent. Okay, now we have to calculate molar mass beta. What I'll do, I'll just transfer M2 here, okay, and that delta B over here. So now we have new formula for capital M2, means molar mass of solute. So it is equals to Kb, or 1000 we have to write first because it is in number form beta. So I am writing number first. So it is 1000 into 1000 into W2 into Kb divided by delta TB into W1. So this is the formula. Okay, everyone. So on that basis, we are going to solve numericals tomorrow. Okay. See here we have the formula, that one. M2 equals to 1000 into Kb into W2 divided by delta TB into W1. Okay, everyone.
Yes, sir.
Yes. So I'm giving you that numerical, just put the value there and just try to solve. Okay. So we'll meet in next class beta tomorrow. Okay.
Yes, sir.
Yeah.